All right, so in a rare feat, we actually started lecturing on the first day. Can't really remember the last time I actually did that, but we did, and we got into equilibrium there. All right, so like I said, last time we talked about chapter 12, or got a little bit into chapter 12, and we started talking about equilibrium. And as we talked about last time, a reminder that really equilibrium deals with a certain type of reaction, and it's these reversible reactions, which we see again those arrows heading in both directions. And again, as we talked about last time, that does mean that we have a forward direction, and in that forward direction, that is kind of your traditional reaction. The reactants going to products in this case, so A and B are basically going to C and D. As we talked about, if you happen to have started perhaps with just reactants, because of the availability of those reactants, the only option in terms of which way that reaction is going to proceed is in the forward direction, because really there's no products to come back the other way. So as this reaction continues to proceed in the forward direction, going from reactants to products, at some point, like we mentioned last time, you will eventually build up enough products that they will actually come in contact with each other. And that's going to sort of initiate the reverse reaction, which is going from products back to reactants in that case. And this will eventually continue to happen until it reaches, as we talked about, what is chemical equilibrium. And a reminder that chemical equilibrium, as we were talking about, does not mean that you have equal amounts again of everybody on each side. What it really is referring to is sort of a kinetics property, which is rates. And that is the point where the rate of the forward direction will basically equal the rate of the reverse direction. And as we talked about last time, what they'll essentially do is lock everybody into place in terms of their concentrations, for example. Again, because just as quick as sort of reactants get used, they kind of get pushed back the other way. And ultimately, there's not much change happening to their concentrations. If you're dealing with gases as well, and sometimes we do with equilibrium, that also would mean that everybody would really lock in terms of their pressures, as you really are not changing how many gas molecules you have sort of on either side. So the pressures will actually lock into place as well if you're dealing with that. Remember that equilibrium is dynamic in the sense that although when we may look at it on the macroscopic level, kind of the big level, it may appear that nothing's happening. Again, if you were kind of to super zoom in, you would see a lot of activity. You would see in this example, a lot of A and B going to products and a lot of C and D going backwards to basically maintain that equilibrium. So again, it can very much appear when you're just looking, for example, at a beaker, a test tube, whatever it may be, that not much is going on. But again, there is actually a lot of activity to kind of maintain kind of where it's at. So it's constantly going forward and it's constantly going in the reverse direction. Just again, their rates are going to be equal to each other. Any questions on any of that stuff there we talked about last time? Okay, so we looked at one sort of example, and I think where we left off was here, I think. So in this case, consider this reaction mixture again that has reached equilibrium. In this case, we want to think about what's going to happen with everybody's concentrations here if we decided in this case to add some more H2 to the mix. So take a moment, think about everybody and decide, what should happen to everybody's concentration. Should they, and much like we sort of talked about last time, we at this point really do have a system that's at equilibrium. So the rate of the forward direction and the reverse direction are going to equal each other. And at this point, we're going to add more H2. So if we think about where H2 is, it's over here. And when we do add more H2, which in this case is a product, should that kick off the reverse reaction, the forward reaction? Which way should go? Should go the reverse way in this case. Again, the availability now of our products is a lot more than our reactants. So they're not going to really struggle to find each other and really start this reaction off. And that would initiate really this reaction heading towards the reactant side. The result of that is obviously if it's moving in that direction, in order to go in that direction, we do need to use our products, right? So for our CO2 in this case, we should see its concentrations start to decrease, right? Because we're heading kind of in the left direction. In the cases of water and CO, we should also start to see those guys start to go up, right? And again, because we should be making more of those guys. And as we talked about last time towards the end there, with H2, we will see probably a couple of things happen to it. Clearly, because we're adding it, we will artificially see it really jump up. But really, the overall sort of way it's going to eventually go, it is definitely going to also work its way back down, as it's going to be needed to react with CO2 in this case, right, to head in the reverse direction to make our reactants. Any questions on that there? Yeah. Yeah, it kind of depends again, kind of how much you add in and stuff like that. But probably in most cases, like we talked about last time, it probably will end a little bit higher than it started with, only because you artificially added it. But if we're looking at sort of what's going to be happening overall, kind of what's happening with this concentration, it spikes because we added it. But again, it will really be working its way back down as that reverse reaction is happening. But you are correct. If you're sort of measuring it, you may see that guy actually end up higher than what it started with. Yeah. Other questions? Okay. All right, there's that reaction we looked at last time. And a reminder that when we do see something graphically like this in terms of equilibrium, we can see, as we talked about last time, our reactants here are starting to decrease. At the same time, again, our products are starting to increase. And at some point, sort of the increasing and decreasing of everybody will start to sort of level out, as you can kind of see in these areas here. And ultimately, they will completely level out. And that's where that, again, dotted line is. And where they all sort of plateau to the end there, that is going to be where equilibrium has reached. Again, they're going to be able to, at that point, maintain their concentrations. That would also, again, be the point where the rates of that forward reaction and reverse reaction will basically equal each other. So let's talk about the equilibrium constant. Now, when we look at a reaction like this, which is a reversible reaction, we could actually write the equilibrium constant, which is capital K, and that is the equilibrium constant. I say capital K because lowercase k is the rate constant in kinetics. Yeah, so lowercase k is actually the rate constant in kinetics. But here we're dealing with capital K. Pretty much this class is brought to you by the letter K. Yes, we're going to talk about every K again that you might not even want to know. And there actually is a relationship that occurs when we have an equilibrium reaction like this that we could do. And really, to sort of write the value of K, we essentially take the concentration of our products divided by the concentration of our reactants. And if you're not sure, the little brackets there means concentration. And for the most part, that is our friend molarity, right? Which is moles per liter. Yeah, so that's usually what we're talking about in this case. So in this case, there's also a really important thing that we do, which is we do take the coefficients as the exponents when we do that. So the concentration of NO2 here would be squared because of the coefficient, divided by the concentration of our reactants. Here, the coefficient really is 1. And much like most things in chemistry, we don't put 1 down usually. So if you don't see anything there, you could assume that it is 1. It does equal 4.63 times 10 to the minus 3 in this particular reaction. The number is really not that important for our purposes right now. So in general, when you calculate the equilibrium constant, you take the products divided by the reactants, and you do use the coefficients from the balance equation as the exponents when you do that. So the equilibrium constant is a really important thing. One of the things that's different than maybe a lot of things in chemistry, which is it's actually just a number. So the equilibrium constant typically does not have units associated with it. It's basically just a number. The number helps us understand, as we will talk about, maybe what is going on in that reaction. So for example, if I have a large value of K, that would mean when I reach equilibrium, would I mainly expect to have reactants or products present? Yeah, just mathematically speaking, right? If it's products over reactants, large number on top divided by small number gives me a large number, right? So basically, if you have a large value for K, what that's going to tell you is when that system reaches equilibrium, you should expect perhaps to have mainly products present. Now, if you have a small value of K, it basically will mean the opposite. When you reach equilibrium, you would expect to have mainly reactants present. Again, same mathematical approach, small number on top divided by larger number gives me a small number when it's all said and done. There is definitely extremes to sort of large and small, as we will see as we go through the different chapters. You can have one that is extremely large, which basically means it is going to pretty much all go to the products. And you could have one that's super, super small. So extremely large, like times 10 to the 32, or like extremely small times 10 to like minus 36. Yeah, super small, super large. And anywhere in between, you basically could have an equilibrium constant value. But at those extremes, again, it will either go one way or the other mostly. But even in those extremes, where you have a really large value of K or a really small value of K, it is still a reversible reaction, which means even though it may all pretty much be going to the products, there is still going to be a smidge of it that's going to head back the other way, either no matter which way you're sort of going in that direction. So even though we could almost consider it a one-way street, it is still a reversible reaction, even at those sort of extremes, that it will still come back the other way a little bit, not very much in a lot of cases in that situation. What do we consider a large value versus a small value? Well, clearly it is everybody's favorite large number, 1. Yeah, so 1 is considered a large value. Anything above 1 is considered a large value of K. Anything less than 1 is considered a small value of K. So if you see an equilibrium constant value with a negative exponent, probably going to consider it a small value. And obviously, if you see kind of anything above 1, which would be a positive exponent or a whole number, if you will be a large value. Questions on that there? Now, a couple other important things as we'll talk about as we go through this chapter about the equilibrium constant, and that is it is specific for the reaction the way it is written. So when you see, for example, the K value for this reaction is 4.63 times 10 to the minus 3. That value is specific for exactly how that reaction is written, with N2O4 on the reactant side, NO2 on the product side. So it is specific for the reaction exactly how it is written and at that temperature. As we will talk about, temperature is the only factor that can affect the actual value of the equilibrium constant. That is why it's called a constant, right? So it's a constant number no matter what you do with it. So as long as you do not play with the temperature every time you do the reaction, you will end up with the same equilibrium constant. Now, the temperature value is really important, and it does affect the value of K. And another really important concept that people struggle with is this. It is a constant value if you keep the temperature the same. And what I mean by that is it does not matter if you started with all reactants, does not matter if you started with all products, doesn't matter if you started with a little bit of reactants, a little bit of products. It doesn't matter if you did more in one reaction of reactants and less in the next. It really doesn't matter as long as you keep the temperature the same. In all those situations, you should end up with the exact same value of K, no matter what you start with. Now, you may be thinking, how can that be? If I start with a lot more reactants, how can I end up with the same value of K? So a really simple explanation of that is It's basically a fraction, right? So let's just say I wanted my K value to be 2, right? I could get 2 by taking 4 divided by 2, that is 2. I could get 2 by taking 2 divided by 1, that is 2. I could get 2 by taking 8 divided by 4, that is 2. They all equal the same. They're not all the same number, right? So regardless of what you start with in terms of reactant concentrations or product concentrations, they will always come to rest at equilibrium with the same proportion of products to reactants that will give you basically the same equilibrium constant. So everybody thinks like when they do the same equilibrium reaction and they do 3 trials and they're using different amounts in each trial, that they should end up with a different K, but they don't. Again, the proportion of products to reactants will always end up the same, regardless of how much you start with. Any questions on that there? Yeah. It is. Of what you start with, for example, of like initial concentrations. So for example, we're going to do, say, that top reaction. And one time we started with 5 molar of just the reactants. And the next experiment, we did it with like 2 molar of the reactants and like 3 molar of the products. Or the next experiment we did just starting with, 4 molar of the products. When each of those systems reach equilibrium, you have their final concentration, their equilibrium concentrations, and you take the products divided by the reactants, it will always hit the same number. It should hit the same number. Obviously, if you're doing an experiment, should be relatively close. But the idea there is it should be pretty much the same number. That's yeah. Other questions on that? Now, when we calculate the equilibrium constant like we did here, which is taking the concentrations of our products over reactants, sometimes people specify this K value as our first one of the season as the Kc value. I'm going to go with concentration for C, seems right. And when you do the equilibrium concentrations and you calculate the equilibrium constant, sometimes it is referred to as the Kc value. And we'll have a lot of K values before we're done with this semester here. By the way, that also brings up a really good point. If you are going to calculate the actual numerical value of the equilibrium constant, you need those concentrations to not be initial concentrations. They need to be the equilibrium concentrations when the reaction is over in the sense of it's reached equilibrium. Yeah, so you can't put initial concentrations in there. Well, you could, but you'll probably get it wrong. But it needs to be equilibrium concentrations. Any questions on that there? All right. There's the equilibrium constant in case you don't like A, B, C, and D. You like J, K, L, and M. I'm doing the alphabet here, I suppose. All right. Now, as I just mentioned a second ago, really, there are no units associated with the equilibrium constant, but it is a very useful sort of value in the sense that it does give you a fairly good idea as to when you do reach equilibrium, what you should expect to occur. As I also mentioned, again, there's sort of different degrees of that. You could have, again, a very large, very small, or you could have something that's not very large or very small. So you can't hang around that one-ish area where maybe you might end up with not a big difference in reactants or products going on. It's not really favoring one side or the other, as you may have a relatively small difference in terms of products versus reactants. So here, if we look at this reaction, and we got Mickey Mouse starting his day there, plus a couple extra circles, and then Mickey at the end of the day just needs a rest. He's upside down. And we have an equilibrium constant there of 25. When this reaches equilibrium, would we mainly expect it to be reactants or products? Yeah, so again, 25 is considered a large value of the equilibrium constant, as all you have to do is get over 1 basically for it to be considered a large value. And we would expect products to be there, or mostly products, a good amount. Now, when we have a homogeneous equilibrium is the same idea as a homogeneous mixture, which means everything looks the same throughout. And a homogeneous equilibrium means that everybody's in the same phase, basically. So if we look at this reaction here that we saw earlier, each of those guys are in gas phase, basically. So we can absolutely write our equilibrium constant, which is known as the Kc, using concentrations. But of course, when we're dealing with gases, we oftentimes deal with our friend pressure, right? Dare I say PV equals nRT, yeah, a little ideal gas law. A reminder of the ideal gas law here: pressure needs to be in atmosphere, volume needs to be in liters, N is moles, T is temperature, and our friend Kelvin. By the way, that's a temperature in Celsius plus a 273 to convert that, right, to Kelvin. And R in this case, 0.08206 liters atmosphere Kelvin mole. Or if you used a rounded number, 0.0821 is all right as well, I suppose. That's the one they beat in my head and I can't get it out, so I use that one. So we can actually write an equilibrium constant expression dealing with pressures, and it is the partial pressure here of NO2, our product, that's squared. Again, we still need to take the coefficients into account when we do it with pressures as well, divided by the partial pressure of N2O4, and that expression is what is known as the Kp value. So 2 slides in, we got 2 K values. Good so far. So that is P for pressure I'm going to go with. Seems logical. We'll go with that. And in this case, you can calculate the Kp value for a reaction. Now, in general speaking, we're going to talk about some calculations obviously later on in this chapter, but usually if you're doing some type of equilibrium calculation that involves pressure, it should usually be done in atmospheres in a lot of cases. So again, atmospheres is sort of the unit that in most cases you want to use if you're doing some type of equilibrium calculation, like we'll do a little bit later on as well. A reminder, 760 millimeters of mercury equals 760 torr, and that equals 1 atmosphere, I believe. Yeah, in that case. Now, is the Kp value and the Kc value equal to each other? They can be, but in most cases, they're not going to be the same numerical value. In a rare case, just mathematically speaking, they can actually end up the same. But in most cases, they will not be the same value. But they will tell you the same thing. So if you have a large Kp value, it means the same thing as you have a large Kc value. It means when you reach equilibrium, you mainly have products. And those products probably are the ones supplying most of the pressure, those gas molecules flying around. And if you have a small value of Kp, it means you mainly have reactants, and same idea, you mainly have those reactants as the one probably supplying most of the pressure that you see. Now, in certain cases, you may be given enough information, for example, to calculate the Kp. So maybe you're given some equilibrium pressures, or maybe you're given something like some equilibrium concentrations and you have enough to calculate the Kc. And maybe you actually want the other value. So maybe you could get to the Kc but want the Kp, or vice versa. There is a formula that allows you to go between the two, and that is the formula right there. The Kp is equal to the Kc times RT delta N. And by the way, you are responsible for formulas in this class. Not that there's a lot up front, but you are responsible for these. So what are all these? The Kp obviously is our equilibrium constant for pressure. The Kc is our equilibrium constant for concentration. R is our gas constant there. So that is R right there. T is our temperature. Once again, needs to be in Kelvin. And delta N is the number of moles of gases. And you want to do products minus reactants. So anybody with a G, you want to add them up on the product side. Anybody with a G there on the reactant side in terms of a state, you want to add those guys up and take the difference. It is really important that you do that correctly. So what I mean by that is, let's just say we had this reaction here. We had 2A goes to 3B. That is really badly done. So let me actually put another letter in there. Let's go with 2C. I know my alphabet, I think. There we go. Let's do that. I'll fix it. So if we take our products minus reactants in this case. The change in the moles of N, you count that by just taking the coefficient, right? That's basically how many gas molecules you got going on there. So that is 3 minus 2 plus 2, 2 and 2. That is 3 minus 4, which is -1, yeah? Is the negative important in this case? I'm going to say yes, and that's because when you look at this equation, for example, this part of it, the RT delta N, when you do it mathematically speaking, and you take it to the -1 versus I just take the difference, which is 1, mathematically you need to do something different with the negative, right? It's 1 over it, right? So it's really important to make sure you do it products minus reactants. And if you do get a negative, it's going to affect the math part of it that you do. So it's really, really important to make sure that you do that. It's a very common mistake that people just kind of take the difference and use the number and kind of ignore the negative if it's there. So you don't want to do that. Otherwise, mathematically, again, you will get the wrong answer. Any questions on that there? Now, when we have a homogeneous mixture, or equilibrium really, there are certain things that we really do not include in the equilibrium constant. Now, a couple of things that we don't include in the equilibrium constant are really anything that is a pure liquid, like water in a lot of cases, or as we'll see later on, anything that is a solid. So anything that is in the liquid state or the solid state is really not included in the equilibrium constant. So for our K, we do not include no liquid or solid. That really means in terms of the equilibrium expression, there's two things that always get included. That is things that are in the aqueous state, aqueous meaning water environment, yeah, the AQ, are things that are in the gas state. So aqueous things, gas things do get included. Why do we not include the others? It's because things that are pure liquid like water, their concentration really doesn't change over the period of the reaction. So it remains relatively constant. So we don't include it. So if we were to write our equilibrium expression for this reaction, dare I say acetic acid plus a little bit of water, making some acetate and a little hydronium ion here. In this reaction, we do our products over reactants, which would be our products here over our reactants, giving us this equilibrium expression. Once again, our water here is going to be constant, so we actually don't include it. So really, if you were to write the equilibrium constant for this reaction, it should be what you see there, basically our products over our reactants. And again, excluding the water, which is a pure liquid. Solids we don't include either because you can think of it like a rock. It's going to float to the bottom and not do much in the solid state. The only way that solid could participate is it has to dissolve itself. And at that point, it's no longer a solid, it's aqueous. So now it can participate, yeah? And so that's the reason for that, yeah. The apostrophe means in this case, it's kind of a prime that this is technically, if you're going to write the equilibrium expression, you include everything products or reactants. But really in this case, this is a constant, so we wouldn't want to include it. So that gets us to really our true equilibrium expression here, which is the one without the apostrophe and stuff, yeah. Yep. And that's why what I crossed out over here is basically that guy times the H2O because that's constant. They'll cancel out each other when you multiply them together. Yeah. Other questions? So as I mentioned before, in general, we do not include any units. It should just be a number that will allow you some information. All right, so I want you to take a moment here and write the KC or KP if possible for each of these. The expression, these are both reversible. So let's take a look. We'll start with the first one here. So we're going to write our KC here. Once again, it is products over reactants. So we're going to take the concentration of our NO2, which is our product. Once again, we do need to take it to the fourth power because of the coefficient that's there. We're going to times it by O2. Coefficient there is 1, so we don't obviously need to put the 1. divided by our reactants in this case, which is our N2O5. Once again, here we will need to square it because of the coefficient there. A question on that one there. For this one, can we write a KP? This top one, we definitely can because they're all gases. So that seems good, right? Gases, pressure. So you can write a KP in this case. You do need gases to write a KP, right? So if you don't have gases, you probably got nothing causing pressure. So you can't really do that for those guys. But this one, they're all gases. So we could do the same thing. We're going to take the partial pressure to the fourth power of NO2 times the partial pressure of O2 divided by the partial pressure here squared of N2O5 in this case. Any questions on that there? For our bottom one here, we're going to do our KC. So again, our products there are H3O plus times our F minus. Each of those have a 1 for the coefficient, so we don't need to put the 1. It is assumed to be 1. Divided by our HF there. What about the water? Do I include the water? I don't. Again, it is a pure liquid, so we would not include it here. Do I write a KP for that one? No, there's no gases, right? So you can't really do that sort of deal. Yeah, so you got to at least have some gases there, or some gas and solid combination or something like that. You need something like that. Any questions on that? Yeah. Yeah. No. So, yeah, yes and no. So for either K, any K that you come across, what should be included is anything in the gas state or the aqueous state. For KP specifically, you can't really write it if you don't have gases. So that one you do need gases present to do that. Otherwise, there would be kind of no pressure or something like that. Yeah. You can probably, in the case of that, you would probably maybe have something, maybe it's a solid or something, wouldn't be included, so you might have something, for example, that might decompose, right, and produce some gas, something like that. So you got something like potassium chlorate, which is a solid, and you heat it up, and then it will form actually a gas and stuff on the other side. So some oxygen gas or something like that. So it's possible you could have a combination like a gas and a solid, and you could write a KP for that. It would just be the one that's a gas in that case. But if you have no gases like we have here on the bottom one, then you can't really write a KP value or a KP expression. Yeah. No. Yeah. So, well, I'll put it this way. You shouldn't do that. So when you're asked just to write the expression, like in this problem here, the KP and the KC, if you're asked to write any equilibrium expression, you should just do it based off the balance equation. So that's just where it should come from. Yeah. And that's sometimes, and I say no for a reason, because sometimes when people are asked that question, for example, they put that down for the expression part of it, the formula, and that's technically not the KP expression for that. That's the formula that go from one to the other in sort of a calculation. Other questions? Okay. Now let's just say, for example, speaking of some other things that could possibly happen, let's just say, for example, here that you had something that we'll do it this way first. I think we'll do like a solid that goes to something that's, say, a gas. We could write the expression like I was mentioning before. In this case, the K would be just the concentration of B, as we would not include the solid basically in this case, right? Now, if you had something, say, the opposite move, where you had this going to, say, oddly, something like this for some reason. Now, in this case, we don't have anything there, right, that we want to include on the product side, but we do want to include something on the reactant side. So in this case, we would do 1 over A and just take 1 for the product side. So if you have something on the product side that you can't include, but you do need to include in an equilibrium expression, something on the reactant side, you just do 1 over basically the reactants. And obviously, if you have nothing that should be included on the reactant side, it's all products, then it's really not a fraction at that point. It's just going to be whatever's on the product side. Yeah. Any questions on that there? Okay. All right, let's try some calculations here. Got an equation. There it is. The equilibrium concentrations for the reaction below for carbon monoxide and molecular chlorine is 0.012, 0.054, and 0.14. We want to calculate both the Kc and the Kp values. So grab a calculator, see what you come up with here. We'll talk about it here in a second.
Express like the charge.
The brackets in this case actually represents just the concentration. So if it did, it would actually be just like you would write Na plus inside the brackets. Yeah, so it's not like a Lewis structure or anything like that. It's like it's more just like the formula of it. Yeah. All right, so let's take a look and see how we're doing. So clearly I want the Kc, Kp. It would make sense to solve for which one first in this case. Yeah, since we have concentration, so that would make sense to solve for that one. So we should start with the expression here. So we're going to do a little products over reactants here for our Kc. So that's going to be our CoCl2 divided by our CO times our Cl2. And we're looking for what that equals. Now, in this particular case, we are given the equilibrium concentration. So as I mentioned before, they do need to be equilibrium concentrations, which they are. So we could just plug and chug at this point into here without changing the problem. There we go. And there it is, 0.14 divided by our CO, which is 0.012, and our Cl2, which is 0.054. Punch that into our handy dandy calculator correctly. Be good. Remember, if you got multiple things on the bottom, don't be afraid to hit that equal sign twice, multiple times, like 0.14 divided by 0.012, and then hit equals, and then divided by 0.054. If you do that correctly, like a 216.0493827, that's a lot of numbers. First off, any question on that part there? Little sig fig action, maybe. A little 2 happening there. Maybe a 220 for old time's sake. Yeah, I'm going to sig figs. Any questions on that there? Now that we do have the Kc value calculated, we can then calculate, I get my thing moving, our Kp by using that formula there that we saw. Kp equals our Kc, a little RT delta N action. So here we do need to convert our temperature, much like most things in chemistry, into Kelvin. So that's a 74 plus a 273. This is a 347. 347 Kelvin. Our R is our constant that we saw earlier, 0.08206. And obviously we just calculated our Kc there. So the last thing we need is our delta N in this case. That is the moles of our product minus the moles of our reactant. Here, anything that is a gas is what we're looking at here. So on the product side, we have just one gas molecule, minus on the reactant side, one gas molecule there, plus one there, gives us 2. That's going to be a negative 1 here. Once again, as we talked about a second ago, that negative is really important for the math part of it. So we'll pop our number in here. You're used to 216 or the rounded number. So we'll go with the rounded since I circled it. Why not? We're going to go 0.08206. We got a 347 to the minus 1. By the way, mathematically, what part should I do first? Yeah, I should do what's in the parentheses first, right? And then take it to the negative 1 and then multiply it by the 220. Yeah, so make sure you do that part first. So we'll go 0.08206 times our 347, do a little 1 over that, and then multiply it by 220. And that gets you a 7.7 perhaps as the Kp value. If you use the 216, you might get to 7.6, I suppose. Question on that one there. So once again, a very common mistake when people use this formula is they kind of multiply the 220 in first and then do the exponent. So make sure you do the parentheses first and then multiply at the end. Yeah. Any questions on that? By the way, this K value is large or small? It is large. Both of them are considered large, right? So 220 is definitely a large K value for Kc. And here you can see again, in most cases, this is the situation. They're not going to be the same numerical value, but we also got a 7.7 for our Kp value, which is also considered a large value as well. So they both will tell you that sort of same idea at the end there. They both should sort of agree with each other in terms of large and small, in terms of what you calculate. Any questions on that one there? All right, let's try another one here and see. I think I fixed it on your notes. I don't know if I fixed it, but we'll go NO2 on this one. All right, so we're looking for the Kp in this case. No, the Kp is actually given to us. The Kp is 158. We're actually looking for what is the equilibrium pressure of O2 if we have some equilibrium partial pressures of NO2 and NO being 0.4 and 0.2. Okay, so let's take a look. So obviously in this case, we're given the Kp. We're also given some equilibrium pressure, so clearly Kp is where we want to start. So we'll start with our expression here. Our Kp in this case, again, should be our products over our reactants. That would be the partial pressure squared because of the 2 there of NO times the partial pressure of O2, coefficient there is 1, divided by our partial pressure squared of our NO2. In this case, that does equal 158 in this case. At this point, we could plug in really our values if you want. We got, in this case here, our NO, which is 0.27, and that's going to be squared, times the partial pressure of O2 divided by our NO2, which is 0.4, also squared, equals 158. We're going to multiply what's on the bottom to the other side. And then when we're done with that, we're going to divide, right, the guy over there to the other side. So we do all that carefully here. 158 times 0.4 squared. Hit equals, divided by 0.27 squared, hit equals. And again, here we will get basically that the partial pressure of O2 will equal about 347. We do need units here because this is a pressure, and it will be the same units as obviously the other pressures in this case. Yeah. Did a little 3 sig figs there since everything looked like 3 to me. Yeah. Any questions on that one there? This value of K is small or large, right? Means mainly we should have reactants or products at equilibrium. Yeah. And since we mainly have products, we should probably expect the pressure of those products to be pretty good. And I would say 347 is pretty good for sure. Yeah. So that all, again, just sort of makes sense in terms of when you think about your numbers and stuff like that. Any questions? Now, as we sort of touched upon a little bit earlier there as we were doing it, once again, you can have definitely a heterogeneous type of equilibrium. And heterogeneous, much like heterogeneous mixture, means you see different layers. In the case of heterogeneous equilibrium, means everybody's in different phases. So in this case here, in the example, we got a little calcium carbonate that decomposes basically into calcium oxide and also some carbon dioxide gas, like we were sort of talking about a second ago with the potassium chlorate. And in this particular case, we would write our equilibrium expression if we just kind of followed the rules like we talked about, products over reactants. But as I mentioned before, since we basically have some solids here, we don't want to include them because, again, they're just kind of sitting there, really not participating. And like I mentioned earlier, the only way really they can participate is either to become a gas or become aqueous. And at that point, they're no longer a solid. So we would not include in this case our calcium carbonate or calcium oxide. And that will give us, much like we saw before, really our true equilibrium expression here, which is really just that one product over there. So the concentration of CO2. Because that concentration of CO2 or the CO2 itself is a gas, that does allow us for this reaction to also write a Kp expression. So here's, I think was an earlier question. We got a little mixture of some states, but we do have at least one gas there. And that does allow us to write a Kp in this sort of case using that gas. And As we mentioned earlier, we kind of jumped a slide a little bit early, but again, solids, liquids never included in the equilibrium expression. Again, pretty much just leaving, as we talked about earlier, two things, aqueous and gas always included in the equilibrium expression. There's sort of the idea there. You can see the solid just kind of sitting there, not too much. You definitely can make more solid or less solid, but the solid itself will basically just kind of sit there and not really do too much. All right, try one more here. Consider the following equilibrium at 295 Kelvin. The partial pressures of each gas is 0.265 atmospheres. Here again, we're looking for both the Kp, looking for again Kp and Kc. So once again here, logically speaking, since we are given pressures, that would be a good place to start, which would be the Kp. So we'll write our expression here. Our Kp will be the partial pressure here of NH3. There you go, times the partial pressure. I'll get it out there. H2S. How about this guy? Am I including this guy? I'm not against a solid, also why you don't have any numbers for him. So that kind of gives you an idea. So in this case, they're both 0.265. So basically 0.265 twice. And that's going to get us there. Yes. About 7.02 times 10 to the minus 2 as our Kp value. Now, in this case, we could then use our equation to go from Kp to Kc in this case. So that's an RT delta N. Our temperature is good to go. It's already in Kelvin, so we don't have to do any conversion of that. We do need to calculate delta N, which again is our moles of product minus moles of reactants. And in this case, we got basically 2 minus 0, which would be 2, as this is a solid and that's one gas molecule, two gas molecules on the right-hand side here. And I think that's everything we need. So we'll go 7.02 times 10 to the minus 2 equals our Kc, 0.08206, our 295. And again, we're going to square it. So here we're going to kind of clean up on the right there, 0.08206 times 295. A little square action there. Gives you something like 586.0127, keeping a few digits. We then obviously want to take this and divide it right to the other side there. So we will take 7.02 to the negative 2 and divide it by that. And that's going to get us a Kc that equals 1.20 times 10 to the minus 4 in this case, right? Once again, in comparison, Kp to Kc, not the same value, but they're both considered small values. And again, they agree, with that. Yeah. Yeah. You do. So basically what the delta N is, it's actually moles of the gas molecules. So that's what delta N in this example is for. So it has to be gas molecules to be included in there. Other questions? Questions on Kc, Kp, had to go back and forth. Yeah. Okay. All right, so let's talk about some other things that we very commonly do with equilibrium equations. Now, sometimes, as you may know, maybe not since they don't teach it in 200A anymore, but you may know that not all reactions do occur in a kind of one-step fashion. They may be a result of multiple individual reactions happening. So sometimes you do need to add equations together. So for example, here, if we have our top equation, we could write our equilibrium constant for it. And if we have our bottom equation there, we could also write our equilibrium constant for that guy. And if we wanted to add these guys together, these two equations, when you add them together, equations, anything that is on opposite sides of the arrow that's the same can either completely cancel out or reduce down. So kind of like subtracting. You probably did some of this when you did redox reactions, right? And balancing those, you got things on every side, subtract it. You can think of the arrow like an equal sign, basically. You kind of subtract it to the other side and get rid of it. And then when you're ready to add it together, whatever's left, everybody on the left stays on the left-hand side of the arrow. Everybody on the right stays on the right-hand side. So you end up with this overall reaction. Now, if we were looking for what the K value was for this overall reaction, and all we have available to us was those two reactions and those K values, we could actually calculate the Kc for this reaction by multiplying these together, basically. You actually don't add them. Now, with energy, you add things, but here we don't add. Delta H's we add, but here we don't add them. We actually multiply the K values together. So in this case, when you would multiply these together, these guys would cancel and would leave you with the overall equilibrium expression that you would have for the equation that has come together, which would be obviously our E times our F divided by our A times B. So if you come across a situation where you're given some information about multiple reactions with K values, and you need to kind of use those K values to build a reaction, you do that a lot with what's known as Hess's law when you're doing it with energy. You basically multiply the K values together to get the overall reaction. So that is one way very commonly that the equilibrium constant is sort of manipulated if you need to. Multiple equations, add them together, multiply. Again, super common error. People always want to add them. So you want to multiply them in this case, the K values. Now, what's another way that sometimes we need to manipulate an equation? And that is maybe we have the equation like we have here on the left, but we actually want the reverse reaction. We want the product starting it going to the reactants with the NO2 on the reactant side. As we mentioned before, the K value that you see is specific for how the reaction is written. So again, the one on the left here, that 4.63 times 10 to the minus 3 is specific for the N2O4 being a reactant. If we were to reverse this reaction, basically just flip it around and have the NO2 as our reactants, we actually end up with a K value of 216, which is specific for NO2 being a reactant and not a product in this particular case. So what is the difference? Well, the difference is we reversed it. So essentially our products become our reactants and our reactants become our products, which means what happens to the K value is it inverses itself. So you take 1 over the K value to get the new one. And that is how you go from this reaction to this K value. So we take 1 over this K value because it's basically the opposite. And you'll end up with the K value for your new reaction. So that also is a very common error that people make. They reverse the reaction, like change the sign, which you don't do that here. You do that with energy, but again, you don't do that with equilibrium. It is 1 over the K value in this particular case. What are some other ways that we can manipulate an equation? Well, some other ways that we may manipulate an equation, for example, is let's say we have the classic A plus B goes to C plus D. Know my alphabet, that's good. And we write our K value here of our products divided by our reactants. And let's just say we were looking at this equation and let's just say, for example, I didn't need 1A, but I needed 2A, right? 2 of A, basically. So in order to turn that 1A in that equation into a 2A, I need to multiply the entire equation by 2, right? So if I multiply this entire equation by 2, that would give me 2A plus 2B. And by the way, when you do that and you multiply by a common number, you should multiply everybody in the equation by that common number, not just one thing. So everybody gets multiplied. 2C plus 2D. Now, if I write my equilibrium expression for this reaction, that is C squared times D squared divided by A squared and B squared. As I go from this guy to this guy, what is the difference in the K value? You only be wrong once if you answer, unless you answer twice. It is squared, yes. So basically the K value just squared itself, right? By the way, if I multiply by 3, the K value would then be cubed, yeah, and so forth. So if you have to multiply a reaction by a common number, you basically take the K value to that common number. So if you multiply by a common number, you take the K value to that common number. Now let's just say, for example, I actually started with this guy, but I only needed one of everybody. Yeah. I basically would be going through this and dividing everybody by 2, right? And when I do that, that's going to return me actually to this equation, right? So when I look at the difference between the K value on the bottom going back to the K value on top, what is the difference between those two? It is the square root of it, yeah. So if I divide by 2, I got to take the square root of K. If I divide by 3, I got to take the cube root of 3. So whatever number you divide by, you take the root of the K value to that. So if you divide by a number, a common number, you take basically the K value to that common number. So in this case, we divided by 2, we would take the square root of it. If we divided by 3, we take the cubed root of it. Any question on those manipulations? I would say those 4 ways are probably the most ways that you would manipulate an equation. Either you would add them together and you need to multiply the k's. You reverse a reaction, you take 1 over the k value. You multiply by a common number, you need to take the k value to that number. And if you divide by a common number, you need to take the root or square root, cube root, whatever root it is, by that common number, basically the k value by it. Any questions on that? Yeah. It is. Yeah. So for example, it doesn't really matter. For example, if I had 2a plus b goes to 3c plus, I don't know, 2d, and the k value is like 50, right? So let's just say I needed 4a, right? So when I would multiply this by 2, I would give me 4a, which is what I need. I still needed to multiply everybody there by 2, and that would give me 4d. And again, because I multiplied by 2, the k for this guy would be 50 squared. Yeah. So it's really that common number, regardless of what the coefficients are. It's important, obviously, if you're going to then add that together with another equation, that you multiply everybody in the equation by the common number, so that when you add the equations together, you get the correct equation that you're looking for. So again, you would not just want to multiply it a by the 2. You got to take everybody in the equation, and then that would be how it would affect the k value. Question on that there. So why don't you try one here? Let's say we wanted the k value for the top equation based on the 2 bottom equations. What should the k value? Since we're getting to the end, let's take a look and see how we all did are doing. So you want to really keep it simple when you're doing problems like this. Sometimes people over confuse it and stuff like that. So when I say about keeping it simple, all you have to think about is just getting everybody to the correct side and making sure you have the right amount of everybody. So what I mean by that is, in the equation we're looking for, I got E on the left. So I'm just going to look for which equation has E in it, which is the bottom one. And in this equation, E's on the right. So I know for sure I need to reverse the equation, right, to get E to the correct side. I also know that I don't need 1 E, but I need 2, which means I also need to multiply that guy by 2. So if I first reverse the reaction like so, that will give me this reaction. And we do want to keep track of our k value, make sure, we kind of do what we need to do there. So when I reverse the equation, I need to take 1 over the k value, right, to do that. I then need to multiply this by 2. And once again, we're going to multiply everybody here by 2. And that will give me 2, 2, 2, and 2. Now that I multiplied it by 2, I then need to take my adjusted k value and square it, right? So again, we want to kind of keep track of all that good stuff. For the next one, that puts the F on the right side now. So that took care of the F for us as well. So we go to the other side, I got A that's on the right-hand side. I have A here on the left-hand side. So I definitely need to reverse that reaction. And in this case, I just need 1A, which is what I have. So for that top equation, I just need to reverse the reaction, right? And when I reverse the reaction, once again, for that K value, I also need to go 1 over the K value. I'm out of equations at this point, so I should have hopefully done this correctly. Let's just double check. We're going to add these together. Anything on opposite sides of the arrows that's the same will cancel. 2C, 2C will cancel. 2D, 2D will cancel. Whatever's on the left-hand side of the arrow will stay there. So that's a 2E plus a 2F. Whatever's on the right-hand side of the arrow will stay there, A plus B. That looks like a winner in terms of my overall reaction. I'm just going to give these numbers just to keep track of what we're doing. So that's K1. I'm going to call it K2. It doesn't really matter. In the case of the K for this guy, we do what with those? Add or multiply? We do multiply. So we do want to multiply those two values. So if we do a little work on that, so we got 1 divided by 20. Going to do a little squaring of it. Going to get an answer maybe. So that will get us 2.5 times 10 to the minus 3. And 1 divided by 100, going to get us our, we'll do a little scientific notation too. Why not? 1 times 10 to the minus 2. So we're basically going to multiply those guys together. And 1 times 10 to the minus 2. And if I do that there, it looks like 2.5 times 10 to the minus 3 would be my K value for the overall reaction. So when you're doing something like this, again, you just want to kind of keep it simple. The simplest way is just to get everybody to the correct sides, make sure you got the right amount. And really the trick of it is to keep track of what you're doing and also make sure you keep track of adjusting the K values for each of those. And the bigger trick is, remember, in this case, you need to multiply, not add. Yeah. It is a 5 on my calculator, but a really badly written 3 there that was supposed to be a 5. Thank you. So that is a minus 5 right there. Thanks. So 2.5 times 10 to the minus 5 would be correct. Yeah. Other questions on that there? All right. Good place to lay it up there.